In this problem, we're going to do a vapor-liquid equilibrium calculation that involves adding one component, which is the more volatile component, to a mixture. See what kind of effect this has, and we have multiple choices for the effect. But we'll actually go through and do some detailed calculations here. First, what we want to do is draw what our initial configuration looks like for this system. Now, we notice we're going to be at constant temperature and pressure, and so one way that we can envision this is that we have a piston cylinder system where we're applying a constant pressure. We have equilibration with the outside temperature, for example, right, and then we have a vapor liquid system, right, in which we have more of the liquid but it has a value of XA equal to 0.40. In the vapor phase, we have YA equal to 0.70. And then what we're going to do is we're going to add 0.50 moles of A, and we want to know what the final system will look like if we operate at constant temperature and pressure. So in this case, we will start doing some basic calculations to understand a little bit more about the state of our system initially, and we'll try to plot that on a phase diagram so that we can really figure out what's happening in our system physically. Number of moles of liquid is equal to 1.0 moles from the problem statement. We're also given that the number of moles of vapor is equal to 0.10 moles, and that means that our total number of moles is 1.1. Okay. We furthermore are given information on the composition of component A, and so we'll just write down some more of this information. All right, so the number of moles of component A in the liquid is equal to 0.40 times 1.0 moles in the liquid. So we have 0.4 moles of A in the liquid phase. And then in the vapor phase, we have 0.70 times the total number of moles, which is 0.1. And so we have 0.07 moles of A in the vapor. Okay, and so that means that our total number of moles of A in both phases, so I'll talk about Na sub T here, is just summing up those two contributions, and so we have 0.47 moles of A in our entire system. All right, and so then we can see that our value for ZA, which is the mole fraction of A in the entire system, not in any given phase, is equal to this 0.47 moles of A that we have in the entire system divided by the 1.1 total moles that we have in the entire system. And that works out to be 0.427. All right, so that's the mole fraction of A in our entire system that incorporates both the vapor and the liquid. All right, and so one thing that will be useful for us to do will be to plot where we are in a phase diagram. And I'm going to choose to make this a PXY diagram, but we could also make it a TXY diagram. For a PXY diagram, we would expect a shape approximately like this. And this is going to be not drawn to the scale of the problem, but just is meant to illustrate what we're doing. We are given some information on this, so this is X sub A and Y sub A. All right, and we know that we're at some pressure. All right, and the liquid side of this phase diagram, remember, will be the higher pressure side, and here's the vapor side, and in here we have VLE. All right, and we know that the liquid phase has a composition of 0.40 at this particular pressure and temperature that we're at. And I'll try to draw a roughly horizontal tie line here. It's intended to be horizontal. All right, and this is at a vapor phase composition of A of 0.70. All right, and we know that the bulk composition, the bulk composition of the entire system is at about 0.43. All right, and so that means that this is the initial state of our system. All right, we want to find out what the final state of the system is if we operate at constant pressure and temperature. And so we know that we're adding only A to our system, all right, and we will be therefore increasing the composition of A at constant pressure, for example. And so we're going to be moving in this direction. But the question is, how far do we move, or will we still be in the vapor-liquid equilibrium regime? And then how much will our liquid and vapor levels be when we add this half mole of A? All right, so let's go to the final state of the system. Okay, so we add this 0.50 moles, and then we know now that our new value for N total is equal to what we started with, which is the 1.1 moles plus 0.5 moles. And so we have now a total of 1.6 moles in our system. Furthermore, know that in the final state of the system, we have a total number of moles of A that, because we added half a mole of A, is equal to the 0.47 that we started with, plus the half that we add. And so now we have 0.97 moles of A. Okay, and so this enables us very quickly to calculate what the Z sub A value should be. Right, and that's equal to the 0.97 moles of A that we have over the 1.6 moles total that we have. And when we divide these two out, we get 0.606, or about 0.61. And so we see that if we move at constant pressure and increase the amount of A, that we move over quite a bit, but not all the way out of the phase envelope. And so we expect that we still, at this same pressure and temperature, have a two-phase system. We just have a lot more vapor in it than liquid. All right, and again, I'm just eyeballing this, but this point, this final point, should be at about a composition of 0.61, whereas if the initial was at 0.43 total mole fraction of A in the system. All right, so now we have the A component represents the majority of the system. Finally, what we were asked is, we can go back to our multiple choice possibilities. All right, and we were asked, we're given some options about what happens. Okay, and one thing that we know is that the concentration of A in the gas phase and in the liquid phase doesn't change because we're still at vapor-liquid equilibrium and we can eliminate C and D. All right, and so we still, in the liquid phase, if we look at our tie lines, we'll have 40% A in the liquid phase. We'll still have 70% of A in the vapor phase, and we're just changing the relative amounts of liquid and vapor when we add A. All right, and so then we need to go see what our other options are, and the other options are that the amount of liquid increases or the amount of liquid decreases. All right, so the best way to determine this is to use this value of ZA that we actually just calculated and then use the lever rule. If we remember from applying the lever rule, what we want to determine is the amount of liquid, which I'll refer to as NL. All right, we want to determine the amount of liquid relative to the amount of total stuff that we have. All right, and so we know we want to determine the amount of liquid relative to the total. And so if we remember from the lever rule, all right, the amount of liquid, if we treat this point, our total composition point, as the fulcrum for our lever, that is proportional to the opposite side of the fulcrum from where the liquid is actually located. And so it's this length, and that length is equal to 0.7 minus 0.606. That gives us the length of that segment along the x-axis. Whereas the total is equal to 0.70 minus 0.40. Okay, so we use the opposite side of the lever if we're interested, so this side right here, if we're interested in the liquid level. If we calculate this out, then I get a number of 0.31. Then it's very simple that the number of moles in the liquid phase is equal to this 0.313 times the total, which we already know is 1.6 moles. We calculated that above. All right, and therefore, the amount of liquid, which started being 1.0 moles, is now 0.50 moles, just a little bit over that. And so the amount of liquid actually goes down, the number of moles of liquid. All right, and this may initially seem counterintuitive that we're adding component A and we're not changing the composition of the liquid or the composition of the vapor, but yet we're decreasing the total amount of liquid by adding A. All right, and the reason that this isn't consistent is what we're adding is the more volatile component. And so it helps to go back up to our system here. We're adding the more volatile component. And so as we do that, the net volatility of the system becomes greater. All right, and so what we'll get in the final state is our system, because we have more of the volatile component, it will have more of an ability to push up and increase the volume of our piston cylinder system. All right, so it wants to be in the vapor phase, and so to maintain constant pressure, the piston has to go up quite a bit, and so the volume needs to increase. And so by making a more volatile system, the net equilibrium results in having actually a lower amount of liquid and a greater amount of vapor. And this is hard to actually determine without doing a detailed calculation. We can tell right away that the fraction of the fluid that's in the vapor is going to go up by the fact that using the lever rule, we can see that we'll be moving in this direction to the right on our diagram. But if you do the detailed calculations, you see that actually the amount of liquid will also go down. And that's because we're enriching our total system in the more volatile component.